Okay, everyone, so we're going to have the second talk for this session now. So this is someone who needs no introduction in the PyData community. So we've got Ozsvald talking about machine learning libraries you wish you'd all known about. Okay, so over to Ian.
Thank you very much. Can you hear me? Is the sound good? You can hear me? Right, before we begin, I need a photograph. I want everyone smiling, please. I like photographs, so smiling and waving. Smiling and waving, smiling back, it's more like it. Brilliant, great, thank you very much. I've lost my clock. Brilliant. I'm going to talk about machine learning libraries that you'd wished you'd known about, because after a year of discovering these, I wished I'd known about them a year before. So I think there's interesting stuff to share here. So some of you know me, some of you don't. I'm an engineering data scientist, so I don't come from a PhD academic background. I come purely from an engineering background into the world of data science, and I've been consulting for 15 years in this domain, mainly back in London. I work with companies like Mitsubishi Finance Bank and Channel 4 and QBE Insurance, doing consulting, coaching, and training around machine learning, data science, or with the Anaconda stack. Lots of NumPy and scikit-learn. I wrote with Misha Gorlick the high-performance Python book, and some of you got a copy earlier on in the book signing. And I also run PyData London. I'm one of the founders there. And I'm super proud of the fact that with PyData London and my wonderful organising team, we've grown in 4 years to over 6,500 members, and we're now planning our 5th annual conference for next year. Now that's very lovely, but you've preempted the clapping, because more importantly than having one large data science group is having lots of data science groups. So I want to thank Tim and the co-organisers here for this being the first year of PyData Cardiff. So can we have another round of applause, please? Right, so I've got to look at the screen because the slides aren't up on here. So goals today, 4 topics to cover quickly. I'm going to talk about regression, but the techniques covered here apply to classification as well. But people rarely talk about regression, and it's quite an important topic, so I thought I'd focus on that. Is my regression working? Why did it make the decision that it made? Explaining the machine learning. Can we make things go faster? I'm a high-performance guy, so can we make things go faster by calculating in parallel? And how can we automate some of the machine learning? And this builds upon the talk that I gave last year, giving an introduction to scikit-learn aimed at engineers coming into machine learning. So you can see last year's talks, a material and notebook if you're interested. And all the material, or most of the material for these slides, is based on the data science delivered notebooks on my GitHub account. So you're welcome to go and follow those, and you can run all the code. So why do we care about explaining our machine learning models to other people? We make a black box, it has great performance, that's it, job done. Everyone should adopt it, make money, make predictions, whatever out of this thing. But that's not how it works in the real world. We need to convince people that this thing actually works, make them confident that this thing is really working well. So helping colleagues gain confidence in a model, particularly helping non-machine learning colleagues, so numerate, smart, but not domain specialist people who know the business domain perhaps, but not anything about data science. Helping them understand the model, that's incredibly important and a poorly understood area in data science at the moment. We can diagnose if examples are working poorly, if some of our data is bad in some way, and we can prove to ourselves that the things that the model says are important actually are important. This is something that I wished I'd learned about many years ago, because I've been puzzled about this for a long time, and now I've found some libraries that make this easier. The example I'm going to use here is the Boston housing dataset. It's a regression dataset. It's a 1970s dataset, back when big data was 500 rows of data. So 500 rows, there's about 13 features. There's only a couple that are particularly predictive in this dataset. LSTAT, that's the low status percentage, percentage of people who are, I can't remember now, I think it's less educated or in manual working jobs. And number of rooms, the median number of rooms in the area around where the house is. So as you'd expect, if you've got lots of lower status people, then houses are probably cheaper in that area. And if you've got properties with many rooms, then houses are probably more expensive in that area. So those are 2 of the predictive features. It's a nice simple thing to get in your head. This plot here from Seaborn plots the median value, that's the average price of the properties, against the LSTAT variable in this case, the low status percentage. If LSTAT is low, off on the left-hand side, your median value is high. When LSTAT is high, there are lots of low status people, then your median value is low. And it's not a linear relationship. It's not a straight line down the middle there. It's a non-linear kind of banana-shaped relationship. So we want to put a couple of these things into a classifier, or into a regressor in this case, and learn a relationship, and then explain it. So first of all, hands up if you know the YellowBrick library. Okay, about 3 of us, right. It's a really good library. More of you should know about it. It was explained at the PyData London conference earlier this year. There's a nice video on that. It helps to visualize, simple visualizers around classification and regression. The one we're going to look at is regressing Y versus Y hat. That's the truth versus the predicted and residual errors. And it wraps up anything that scikit-learn understands. So it can explain any of the models that you can build in scikit-learn. These are the kind of outputs that you get. On the left-hand side, we get the Y versus Y hat, the truth versus predicted plot. So whenever we get a prediction, let's say, take some values around 20 on the bottom axis, the Y. So any truthy values around Y equals 20, so that's houses costing $20,000. If the predictions are $20,000, then you start at 20,000, you go up to 20,000, you get a dot. For houses that cost 30,000, if you predict 30,000, you get a dot. 40 and 40, you get a nice 45-degree straight line. That's the grey dotted line running up through the plot, bottom left, the top right. If all of your predictions follow that line, then all of those dots will be along that grey line. And that best fit line, the darker dotted black line, that's showing us that it's not 45 degrees, it's off slightly. And it turns out here, all the median valued houses are predicted well. They're roughly between sort of 15 and 30,000, and they're predicted correctly. But the higher valued houses, they underpredict. Why do they underpredict? Well, we don't know. At this point, all we know is they underpredict. So things at 40 to 50,000, typically they're being predicted around 30 to 40,000. So something's missing. Either the regressor is underpowered for some reason, or the data's missing. And my money would be on the data not being rich enough to describe the relationship that properly expresses why these properties are more expensive here. We get another plot, this residual plot. Blue dots are the training residual errors. So every time you make a prediction on the training set, you can look at how close the predicted error or the prediction is against the truth value. Those are the blue dots, plus and minus 0 error, which would be a perfect prediction. And you get the green dots, the same on the predicted predicted testing set. If the green and the blue dots are equally well represented, they look they've got the same distribution, everything's good. If your green dots had a different distribution to your blue dots, you might start questioning, well, what's happening with my training data and my testing data? Are they different data sets? Have I mixed up my training years, perhaps? Have I split the data in an arbitrary, weird way? So I'm learning on one set of relationships and trying to predict on a different set of relationships. So here we can start to diagnose whether the model itself is working. But it doesn't tell us what's happening underneath, behind the scenes. So Eli 5, who's heard the phrase, explain it like I'm 5? It's a Reddit thing. All right, so explain it like I'm 5. Please explain quantum physics to me like I'm 5 years old. So take all the big words out and give me the really simple explanation. Eli 5 is a Python library that wraps up a bunch of machine learning libraries, so scikit-learn, XGBoost, LightGBM, and a few others. And it tries to explain some of the important things about the predictions coming out of those models in a really simple way. The kind of simple way that you can show to your boss, who's not a data scientist, and have them understand what it is that you're doing and why this thing is working. So I think this is incredibly important, and I wish I'd found this stuff earlier. Also, Eli 5 and the other library I'll show in a minute, they're only a couple of years old, so this is pretty cutting-edge stuff. So one of the things we can get out of Eli 5 is a permutation importance score, which is a replacement for feature importances. With feature importances, we train our model, a random forest regressor, say here, and then we can ask the random forest regressor, well, which features are most important for making your predictions? And using an internal method that's specific to that kind of tree estimator in that case, and different models have got different ways of telling you what's important, it calculates which features are important, rooms and LSTAT, these dark green things here. Equally important, they've got similar weights according to its calculation. This is the scikit-learn importance measure. If we use the Eli 5 permutation importance, it does a different job, a different way of calculating things, a model-agnostic way of calculating things. So it's the same method that you can apply to any different type of machine learning model. And it tells us that LSTAT's very important, rooms next most important, but not equally important, and a few other things are important. So it gives us a different way of diagnosing what might be important in our data. I think that's pretty interesting. It lets us start to question, well, why do these models, why does the model-specific version think some things are more important, and the model-agnostic version think other things are more important? What's happening? What drives that dynamic? The more interesting thing behind all of this, I think, is that we can begin to explain individual examples. Why did you make that decision for that particular example in my data set? So we train it on a bunch of properties in the training set for this regression problem, and then we've got, in this case, 101 testing examples. And I can point to every single test example and say, justify yourself. Why did you make that specific decision? And a couple of trends come out, and they won't be particularly surprising from a human level because we understand the context of this problem. So expensive houses tend to have many rooms and be in areas where there's a low status percentage, so few of the manual workers, say. And in areas where the schools have good pupil-teacher ratios. Cheap houses tend to be in areas where there's higher low-status people, fewer rooms, maybe there's pollution in the area, and there's a lower pupil-teacher ratio. The important thing to consider here is that in the previous slide, the models are telling us these different ways of looking at the data, saying globally there are two important features. When we start looking at specific types of the properties, it turns out that some things are predicted by features with different importance. So many rooms is more important for the rich properties, and LSTAT percentage is more important for the cheaper properties. So it turns out this is giving us like a local view, not just a global view. And there's a couple of talks at PyData Warsaw just last week, and I urge you to follow up on those links there. There's lots of interesting stuff discussed by my colleagues in those two talks. So Eli 5, we can ask it, show prediction. That's all you do, Eli 5, show prediction. Give it an example to explain, so one row of your data, and it gives you this kind of output. And it says, right, bias, that's the average of the data set. So the average house price, 22,000. Because rooms are 7.8, that's a high number, median number of rooms, add $15,000. Because LSTAT is a low number, 1.9, you can add another $6,000. So it's a high-class neighborhood, we can add $6,000 to the prediction. And then you can see all the additive effect, the contribution on the left-hand side. This is why we're adding money to this prediction to get us up to this $50,000 property. So that's nice. We can look at an individual property and understand why we think that the random forest is making this specific prediction. You can take this a step further. I'm really proud of this plot, and I hope it's just about big enough to see. Here I've explained about 100 properties ranked by their price. So the cheapest properties are on the left, medium ones are in the middle, and then the most expensive are on the right-hand side. That's the bottom plot. And the top plot is all the features that contribute to making those predictions. So it's not all 13, I think it's about 10 features I've got here that are the more important ones. There are two important lines here, rooms and LSTAT, the two features that we know are important. Rooms is about 1/3 of the way down. It's a darker blue line ending with some red dots. So for each of those 100 properties that we see across those columns, most of the properties have a certain number of rooms. That means that their average price is decreased, their price is decreased according to the average by a small amount. You take a few $1,000s off, that's the blue coloring. And then you get some larger properties on the right-hand side, that's the red, where they've got enough rooms that their price is bounced up a heck of a lot. So it's an interesting non-linear relationship. Most properties have a small price influence over most of that range, and some of them just have this huge increase in price because they've got lots of rooms. But there's one anomaly, which I'll mention in a moment. And on the other side, LSTAT, that's the bottom row. It starts deep blue, and it goes to neutral, and then it goes lightly red on the right-hand side. So it's a different kind of relationship. It's more of a linear relationship we're seeing there. The cheaper properties are explained by the low status percentage. That's the biggest driver of their price. It knocks a lot off their price, drags it down. And then the expensive properties, well, when they've got a good LSTAT percentage, you get a small increase in their price because of that, but only a small increase. For the cheap properties on the left-hand side, the top bar is crim, so criminality. If criminality is high in your area, that also drives your price down. And there are other relationships like NOx pollution levels. The interesting thing on the rooms is we get a set of red blocks, so all of these houses are big, and so they drive the price up, apart from the one that's coloured blue at the second to last column. There's a blue bit there. I was puzzling, why is it the case that not all the houses are big and driving the price up? Turns out the one with the blue bit there has only got a few rooms, so it should be cheap. But it's not cheap because of only a few rooms, it's expensive because it has a few rooms and its distance to employment centres, it's a column, a row, 2 rows down, the distance to employment centres is tiny relative to everything else. So I checked a bit further into the data. All the red ones, they're big out-of-town properties with many rooms. That other one, the other anomalous one with a really high price, is a small property inside the employment centres. So I think that's a high-priced apartment somewhere right inside a city. So here you get an intuitive explanation that you can talk through with a realtor and say, this is how the model's working. Do you trust the model's work? And they're going to say, oh, sure, these relationships I see every day. I trust your model. I see why it's doing this. And then you can hopefully have a better conversation about the data and the model's workings without getting specific about machine learning with whoever you're liaising with. There's another tool that I think is really interesting. This is a much newer tool, LIME, locally interpretable model explanations. It takes the notion that for anywhere in a high-dimensional, complicated data set with lots of nonlinear relationships, if you take a particular point that you want to explain, the relationships in the neighborhood of that point are probably linear or linear-ish, linear-like. So if you build some linear classifiers just around that one point you want to explain, you can build some really simple linear models that explain the most important reasons for a decision in that area. So this is a model-agnostic way of explaining your predictions, as opposed to Eli 5 that uses a model-specific way of explaining their predictions. I don't know which one's better. I think they're both interesting, different ways of looking at the data. The more interesting bit to me is, if I've got 2 totally different methodologies for explaining the predictions, and they both agree, well, I probably trust it. If they both disagree, I'm going to be scratching my head and wondering if this thing makes sense. And if it doesn't make sense, what have I got wrong? Because I probably made a mistake, or the data's bad, or the business understanding is wrong, or something is wrong, and I can probably diagnose it. Without using these techniques, all I get is a score out of a model that just says, oh yeah, the model's, yeah, it's kind of good. And I just go, well, I think it's good. I think we should, stick it into production. Let's put £1 million behind this model and hope we make money on whatever we're doing. And maybe I'm wrong. And that's kind of a fireable offense. Here we can start to dig the model apart and try to see, do we trust it? What do we trust? What don't we trust? So if we use LIME, explanations show in Notebook, another simple one-liner. We get an output not unlike the one we saw with Eli 5. It starts to break out. This is for one of the very cheap properties, about $10,000. What contributes to this negative, or this small pricing? We see negative contributors and positive contributors. There are no positive contributors. It's all negative. So relative to the 22,000 average price, because LSTAT is greater than 17.11, it deciles the data per feature. Because LSTAT is so high, you get a huge negative change in the price. Because rooms is less than 5.89, so in the deciles it's the smallest decile, because you've got so few rooms, you knock more money off the price. And you start adding up all of those negative contributions, $22,000 minus each of those, you end up with the $10,000. So there again, we get a different way of looking into our data and explaining why these decisions are being made. Now we're going to jump away from machine learning for 2 slides to look at high performance, because this one saved my bacon, so I wanted to share this one. Who in the room is using Dask? A couple of us? Okay, a couple of us. A few more of you should be using Dask as well, because Dask is actually insanely powerful for some specific tasks. Dask is a bit like Apache Spark done light. So it's a Python-only Apache Spark-like thing. It's a medium data processor. I won't call it a big data processor. It's not designed to be dealing with data spread across many machines all over the place. It's designed to be dealing with data on one or a couple of hard drives that's too big to fit into RAM, but small enough to be operated on a single machine. It does run on many cores, and it can run on many cores over many machines, but I don't really care about that bit here. All I really care about is that Dask works quite like pandas. And that example at the bottom, on the left-hand column, pandas read a CSV file, group by something, group by user ID, and calculate the mean. With Dask, You can read your CSV files with a glob, so put some stars in, read many CSV files, and then do a group by and calculate the mean. And so it does it in basically the same code, but in this case, it'll be reading many CSVs, possibly millions of them. So it's got a very simple pandas-like interface. If you've got a CPU-bound function, and I was using this on a Kaggle competition, the Quora question pairs competition, you have millions of sentence pairs. So I've got 2 columns of sentence pairs. I'm calculating string edit distance metrics. Each calculation, doing it for, say, the Levenstein metric will take about 20 minutes on a single core. And that's the top example, using pandas apply with the Levenstein function, axis 1, calculate it on 2 columns at a time, make a 3rd column as the edit distance. Took about 20 minutes, single core, really boring. So you put it into Dask distributed, n partitions, that's just the number of CPUs available, 8 on my laptop, and tell it to apply the Levenstein function, axis 1, and then all of a sudden, you can see at the bottom, that's htop, that's all 8 cores of my laptop burning away, the machine's going crazy, and I get a 3.5 times speed up. So I get a 3.5 times speed up for free. It just happens just by adding an extra line of code. So that's brilliant. So if you've got CPU-bound functions and you want a really cheap win, have a look at Dask. And yesterday, Victor gave a talk introducing Dask in much more depth, so maybe review Victor's slides. The final thing I'll talk about, TPOT. Who's heard of TPOT? There's a couple of us again, great. So TPOT is an automated machine learning solution. It won't put those of us in the room who do machine learning out of a job. It's a dumb, big for loop that tries to iterate over all the possibilities for machine learning solutions, different classifiers, different regressors, different data preparation steps, and tries to evolve a good configuration without me having to do it by hand. So TPOT, that's an example off their website. You have a TPOT classifier, looks like a scikit-learn classifier. You do tpot.fit, and you give it your data, and it sits there churning away for as long as you tell it to churn away, trying lots of different combinations of different classifiers and regressors and steps. And at some point, you just say, oh, I'm bored, stop. And it says, oh, well, I got 99% accuracy. Human, how good did you do? And if it did better than you, brilliant, you've got a better solution ready. It writes out about 7 lines of code to a file, and you've got a log with all of the other versions it tried. So you can pick up the other versions that it was attempting, and then you can just use them. It just gives you some scikit-learn code. So for a different Kaggle competition, I took 2 different TPOT models in a couple of days, combined them with a third that I read about in one of the forums, combined them just by averaging my predictions together, and I got in the top 50% in that competition, basically for 3 days' effort, basically where most of it was letting TPOT just grind on my CPU and me making coffee. So that was really kind of interesting. I wouldn't suggest that you go into TPOT straight away and try to do automated machine learning. If your data's crap, then this will work really, really quickly, turning crap into crap. And that's no good at all. Garbage in, garbage out. We need high-quality inputs and high-quality outputs. But if you understand your data, you've built some models, you know what you're doing, then TPOT gives you a good way of building a nice benchmark to see if the machine can do better than you can. And probably it can if you haven't put lots of work in yet. So that's quite a nice, just automated approach. Leave it running for a weekend to see what happens. So, closing notes. I think we should all be diagnosing our machine learning just like we debug our code. I come from an engineering background. I really care about getting my code right. Diagnosing machine learning is hard, but now we've got these libraries. They're a couple of years old, but they look really interesting. So if any of you are using them, I'd be really curious to see how you're using them. These slides will be up on my blog by tomorrow. Next year, I intend to do some more public training classes. I'm really curious. I've got a large audience of you here. Please come and tell me afterwards what kind of training you might be interested in, and whether you really want training next year. I want to poll you all to find out what needs to be trained in. What is the UK lacking in machine learning and Anaconda and whatever training that maybe I can help you with. I'm super curious about your thoughts on that. I like drinking beer. I'm happy to answer questions. Questions and beer go really, really well together. So you're very welcome to ask me questions, even better in the pub. And this goes as well, of course, for all the other speakers here. If you see a speaker, if you want to do something nice, buy them a beer, buy them a slice of cake, or one of the volunteers. Go and thank the people who contribute to making this a really good conference. I have an extra request for you. I've never asked for anything from my audience before. I'm going to ask for a postcard from some of you. I've got a gap on my wall at home, a big empty gap. I want to fill it with some postcards from people who say, oh yeah, Ian, that chap, he taught me something. So if it's the case that actually I taught you something now or one of the past talks, and you could go out of your way to get a postcard, either this weekend or when you're on holiday in 3 months, I don't care. Send me an email, I'll send you my address. I want to fill up this block of wall with some postcards from people saying, yeah, sure, you taught me something, thank you. Stick it on the wall. That would be like a physical reminder that I did something useful. That would be really useful. I'd really love it. I really want some postcards, please. And if you want to see more, have a look on my GitHub. That's the Data Science Delivered. There's a bunch of notebooks, including this notebook, which is Diagnosing Regression. That's me. Thank you very much.
Okay, thanks, Ian. Actually, one of those, the Eli 5, my external examiner was an expert on using permutation methods in random forest, so it would have been really nice if I'd known about it, but didn't. But anyway, I think we have got some time for a couple of questions.
Do we? I thought I ran exactly the time. Brilliant, I'll take it.
Maybe we'll take one question.
There's
a burning question.
There doesn't have to be. There could be pub questions.
I think they clearly want to buy you beer.
Well, and everyone else beer, right? All the other speakers beer and all the volunteers.
There we go.
All right, thank you very much.